Thanks a lot, everybody, to inviting me here. My talk will be mainly about chemistry. I am not a physicist, so I will talk about how we preparing the crystals and some application in the field, what we are doing. Since it was here tell a lot about 2D materials for whatever they can be used and how nice they are, I will skip and go directly for the first one. The chromium sulfobromide, it's starting to be very popular material. It belongs to the structure type of iron oxochloride. This compound is already known from the 30s very well. Chromium sulfobromide is first published 1966 and all magnetic basic measurement was done already in 1980. So it's also, at least in the bulk scale, relatively well-known materials, but still it's quite tricky how to synthesize this material and how to handle it. So here is a phase diagram which we recently calculated. You can see that we have some limited temperature stability and peritectic decomposition. So you are limited with some window of the suitable rate of the chemical transport. For the grow can be used multiple zone or two-zone furnace, and then to prepare and upscaling materials for various applications, there is critical the first step, how to make to reacting it. Either you can start with a chromium bromide and sulfide, but they are not always completely pure. So in our state, we typically go directly for most of the synthesis from elements. So when you have in the system very high pressure of bromine, it's really important to keep top part cold, which is not always successful, but it's allowed to use up to 50 gram scale then for the vapor transport growth, which typically take like 2 weeks. And something more about the grow. Here are this Kellogg diagram where you have a region of the stability of chromium sulfobromide and corresponding partial pressure of sulfur and bromine for different temperatures. So you can see at already 1200 degree Kelvin, you have all you need already relatively very high vapor pressure of both elements. And what was most surprising for us, you need 2 orders of magnitude higher partial pressure of sulfur than bromine. When you have seen this phase diagram, you can see that it's decomposing to chromium tribromide and chromium monosulfide plus sulfur vapor. So to keep a low defect system during the growth of chromium sulfobromide, it's better to use as low as temperature as possible and then keep as high as possible partial pressure, not only bromine, but also sulfur, to avoid the defect on the anion side. So by this way, it can be relatively easy upscale the synthesis of chromium sulfobromide, and then this allowed us to use for various applications. We are doing a lot about electrochemistry and printed electronic, so you can use this chromium sulfobromide, the layered structure, to intercalate organic compound. Usually inorganic compounds not work very well because chromium sulfobromide as well as other halogen-chalcogen systems are not so stable towards alkali metal, and you can easily lose this bromine from the system, and then you getting some weird, not explored chromium monosulfide 2D materials. But when you use organic compounds like amines, in this case, you getting either complete exfoliation. These are individual mono and few layer nanofibers. If you optimize, students do it already a few weeks ago, that the scale of the fibers go to tens of micron and even much broader. So this is one issue. It's exfoliation, where you easily get large number of monolayers, but you can see also these peaks which indicate intercalation. So you have CrSBr layers, and inside you are getting bulky molecules, and you completely decoupling CrSBr layers, and then they start to behaving as a monolayers even in the bulk. You can see from the absorption, band gap, and the Raman spectra for this monofew material exfoliated. It can form very stable inks for a couple of months, can be stored, and then used for the fabrication of printed electronics. And here a little bit more results. You can see that if you perform this gentle electrochemical intercalation and subsequent exfoliation, you are getting very nice flakes, which has mono to few layer structure, but always even this would behave as a multi-layer. You can find this amine peak on XPS, which means that inside the layer you still have the layers of amine, so even this quasi-bulk multi-layer material behave as a monolayer, which can be seen from the magnetization data, where after intercalation we are switching from antiferromagnetic material to ferromagnetic material because it behaves as a monolayer, completely decoupled. Since we are chemists and we work on many chemical applications, one of them was to use this layered material as an anode for lithium and sodium batteries to intercalate, and there undergo the decomposition and obtaining chromium bromide, which is also layered, and in the case of lithium sulfide or either sodium sulfide. And what was really interesting, if you use this type of batteries, more you charge and discharge, the better battery is. Usually you degrading it, but if you use chromium sulfobromide, you are improving your battery with more cycling. Because it's a semiconductor and it's relatively well stable, it can be used also for water splitting in alkaline and acidic media. And then what we work on it, we try to prepare this intercalated system stable. So by using of different amines, in the case tetra, or it can be octyl, hexyl, or you can even intercalate chiral-amine, and then it probably will be very interesting optical properties. You can tune interlayer distance. From this TG curve, you see that the stability is around 100 degrees Celsius, then these molecules going away. And also there are some significant change in in-plane and out-plane vibration in Raman. So we try to study a little bit more detail this intercalated material when we perform just relatively gentle treatment. In this case, we take these CrSBr crystals, apply potential, typically negative potential, and large amine cations go inside, and if you perform relatively shorter time, you get this partial intercalation. It's interesting, we still don't understand well, because in the crystals we take from this area by FIB lamella, and you have here an intercalated region and intercalated region, and by TM you can see clearly significant increase of the interlayer distance compared to the virgin area. So by this you can either tune the material properties by changing the distance, but also changing the properties if you intercalating like optically active materials. Another way how to change the properties is doping and alloying. So in this case we try to explore what possible is gets to the substitution for chromium. And it's look like in the periodic table of D elements that others analogs of CrSBr with the chalcogen, sulfur, selenium and tellurium are not so thermally stable. And from all surrounding elements, recently we try also titanium, we try also nickel. Only vanadium is possible to incorporate and substitute just about 1% of chromium. All other elements form just separate precipitate on the surface of crystals in the form of either chalcogens or halogens. But we have more possibilities on the anion side. They're existing in the literature from 1960, was mentioned by a couple of people that they were able to get even the analogs with tellurium and iodine. So in our case, we start to explore what we can get substitution for halogen. It was already published from the Columbia people above 70%, so it's relatively easy to get. Up to now, we have analysis for the 50% substitution between bromine and chlorine. You can continually tune the properties, and thermal stability is almost the same. But if you want to go for the heavier halogen and heavier chalcogen, like with iodine, we start with 10% in the starting system, and only 5 was incorporated. The same systems are also sulfur substitution with selenium and tellurium. Tellurium will be probably finished next week when I arrive back to lab, but for the selenium, substitution to sulfur 10 and 20% was possible to achieve. And if someone gets a sample with 10% of chlorine, it was actually error. It's 10% of selenium in that sample. So another group of interesting mixed halogen chalcogenide are not only from this group of iron oxochloride, where we have a lot of for the oxygen chalcogen, and then for the rare earths, which can substituting chromium, which is relatively unexplored, another 40 analogs of chromium sulfobromide, but for the stoichiometry of 1 chalcogen and 2 halogen, we just 2 months ago grown this compound, which was recently published just for niobium for super high nonlinear optical effects, but it worked very easy also with tantalum and heavier niobium analogs, just mixing the metal oxide and halogen, growing in 1 week very nice crystals, which shown completely perfect single crystalline orientation. So this is this group of compound, and recently we start to work also on some possibilities how to substitute hexagonal boron nitride to found some new alternatives. So in 2001 it was published this theoretical paper where it was predicted a lot of new interesting high-key materials. There are many possibilities, but also a lot of limitation. You have hydride halogenide, which is possible to synthesize, but their stability is extremely limited and by moisture and oxygen decomposing in second. Then you have a lot of some interesting halide like calcium iodide, magnesium iodide, but they are extremely moisture sensitive. But you have also this compound which either adopting metlockit structure, lead chloride fluoride, which is compound known for many hundred years, but due to strong interlayer interaction, it's very difficult to get this PbClF exfoliated. But for the rare earth compound, which are already also about 80 years known, there was predicted relatively high dielectric constant for either an in-plane, out-plane, with very nice band gap and equivalent thickness, which is very nice, comparable to hafnium dioxide. So in these systems, we try systematically to grow all these 40 compound, which around 25 nicely working. And what we find out, that using more heavier halogens, we getting lower interlayer interaction. For the chlorides, it's very difficult to get monolayers. For the bromine, is okay, and iodide analogs exfoliate very well. It can be relatively easy upscaled using molten salt synthesis, where you reacting oxide or putting hydrated compound, like we put there lanthanum chloride hexahydride, and you just heating up in the molten salt system and cooling down on air, and you are getting flake in the millimeter size, which can be then either used for stamping or for ink fabrication. And here you can see for the case of lanthanum oxobromide, the flakes in the millimeter size, the band gap measured by the photoluminescence give value which was close to predicted value above 5 electron volt, and it can be relatively easily exfoliated to the multilayer system. This material was also reported its synthesis by the reaction of halogen with oxide. It's much more complicated. Then you use this lanthan in the case of bromine and lanthanum bromide as a solvent, where you dissolving oxide and then precipitating crystals of oxobromide. Compared to the flux grown, it's like needle shape and not so nicely exfoliated, and also much more complex to make in ampule, where in the crucible in air or just simple argon atmosphere, it can go to 100, even 100 grams. Synthesis, here are TG curves. It looks like the mechanism is first formation of anhydrous bromide, which subsequently reacting with oxygen from the air and forming bromide or oxochloride system. Huge advantage is that these materials can be used easily up to 500 degrees Celsius. So it's high temperature dielectric materials. We use them in collaboration with EPFL and Raskish to fabricate devices, either molybdisulfide or graphene one. And here are the results by the measurement of this shifting double-gated structure, Dirac cone shifting. We get out plane dielectric constant of 9, which is like 3 times higher than hexagonal boron nitride, so it can be named as a layered aluminum oxide. It's comparable to aluminum oxide, but can be easily exfoliated. The breakdown voltage, another important parameter, is slightly lower than hexagonal boron nitride, where it's like state-of-the-art 1 volt per nanometer. In this case of these materials is around 0.8, 0.9, so it's slightly lower. But it can be used also like high-key dielectric environment to fabricate a photonic device, like in this case in EPFL was made a device where molybdisulfide was encapsulated in 2 LaOBr layer, and you can clearly see and tuning the exciton and trion peak. And here is already the comparison for the classical dielectric materials like hexagonal boron nitride or the systems which are typically deposited by atomic layer deposition, and our lanthanum oxobromide, and now also recently popular bismuth selenium oxide. So here is still a lot of stuff to explore, because you have 14 lanthanides, and even the theoretical calculation was done only for lanthanum and holmium. So now our students working to measure the electric constant and breakdown voltage for another 40 compounds in this system, which is a huge advantage that all of them are air stable and can be easily handled even up to several hundred degrees Celsius. And the last part of my talk will be about the common material, hexagonal boron nitride, which everybody using. The typical synthesis is performed in anvil cell. It's the same like people using for study high pressure physics, where you have 2 diamond crystals. But if you're doing it in big scale, it's the same machine like for the diamond. So you have this pressing machine, which is able to make 1 to 510 gigapascals and heat it up to above 2000 degrees Celsius, and by slow crystallization from the flux you are getting hexagonal boron nitride crystals. But you can also apply the metal flux. It was recently published like 4 or 5 years ago, when you dissolving in iron and iron alloys boron and then cooling down in the nitrogen atmosphere, you are precipitating boron nitride. So this procedure can be upscaled and can be optimized by the dissolving of boron nitride in nitrogen-hydrogen atmosphere and slowly precipitation. It's possible to getting high-quality hexagonal boron nitride flakes in the size up to 4 inch in about 4 or 5 days. The difference between the system made by high pressure is there is a minimum of nitrogen vacancies, but since we are working at atmospheric pressure by this method, you dominating with vacancies of nitrogen, not boron, which are typical for high pressure material. And in collaboration with Nathan Wilson, he do for us a lot of statistics on the breakdown voltage. So for this material, typically breakdown voltage exceeding about 1 volt per nanometer, which is comparable to high pressure, high temperature made hexagonal boron nitride. There can be also find randomly several of these quantum emitters, but it will be nice to explore more if it is possible from the flux to dope it and to control formation of some quantum emitters in the system. And here is a comparison of the thickness for equivalent thickness and breakdown voltage for the hexagonal boron nitride, which we growing from the metal flux in large scale, and hexagonal boron nitride, which is reported from the material made by high pressure, high temperature synthesis. So that's all from me. Thanks a lot to staying here until the almost end of the conference. And if you have any question or you need any crystals of 2D materials, I will be happy to share with you. Thanks a lot again.
Thank you for the great talk. Time for questions. No? I would like to ask a question, if not. So you mentioned that for this lanthanum oxybromide, it's air sensitive, air stable.
Yeah.
Like, is there a rule of thumb about, hydride, like moisture sensitivity about this hydride in general? Like, for example, this chromium sulfide bromide, whatever.
So
is also, people say that it's also like stable in air, right?
Yeah. So from the TG curves, even heating on air, which is performed here to study the decomposition and temperature of the formation, this one was on air by the decomposition of lanthanum, hydrated lanthanum bromide. You can see that this oxobromide forming at temperature above 500 degrees Celsius, and it's stable even up to like 800 degrees in air for the limited time.
I see. I had a sense that this halide is general, like, is moisture sensitive, but it's not. It really depends on the materials, I guess.
Yeah, when it's there, oxygen, it's like already partially hydrolyzed, and it's quite stable. But in Vienna Technical University, they now trying low temperature AFM, so they try to condense some monolayer of water, and then they find some absorption. So definitely there will be on the monolayer level, atomic level, some interaction with water molecules. And by this studying using AFM, it can be found there either bromine vacancies, and also depending on the flux used, like when we use magnesium-based system, some lanthanum can be substituted with magnesium, and then it's compensated by the bromine vacancy to have a neutral charge in the system.